Welcome to everyone to our Catalysis webinar. This is our first week, so I'm really excited to kick off our series today with Dr. Bukhryakov from the Florida International University. To introduce myself, I am Lorianne Schultz, and we also have on here Corbin Fiat. We're both from the American Vacuum Society here at the University of Central Florida. And the way that this webinar format will take place is we'll have a 30 to 45-minute lecture by Dr. Bukhryakov, followed by a 10-minute Q&A session. So if you have questions, please don't try and unmute yourself. Please just go ahead and type them into the chat box. And at the end of the lecture, I'll go ahead and read those questions out loud. We might not have time to get to all of the questions, but we'll get to as many as we can. And so I'm really excited to introduce our speaker, Dr. Konstantin Bukhryakov. He graduated from Tyumen State University with a BS in organic chemistry, and then he worked as a research scientist at the Chemical Diversity Research Institute, where he worked on projects for Novartis, Merck, Abbott, Eli Lilly, and others. Dr. Bukhryakov then obtained his Ph.D. at Lomonosov Moscow State University, studying under Alexander Kurkin. And shortly after receiving his Ph.D., he was invited to join the research group of Professor Valentin Rodionov at the King Abdullah University of Science and Technology, Saudi Arabia. As a postdoc fellow here, he developed new catalysts based on amphiphilic polymers, including organo and metal complex catalysts. And then he worked as a postdoc in the research group of 2005 Nobel Prize Laureate Dr. Richard Schrock at MIT. And during his career at MIT, he developed a class of molybdenum complexes that have shown unprecedented activity for cross-metathesis of electron-deficient olefins with unreactive substrates, and established a synthetic route to molybdenum oxoalkylidine complexes. Following this, he joined the Department of Chemistry and Biochemistry at Florida International University in 2018 as an assistant professor in organic chemistry and radiochemistry. And today he's going to share about homogeneous catalysis by organometallic complexes. So I'll go ahead and pass this off to you then.
Hi, can you hear me well?
Yeah.
Can you see my slides?
Yeah, we can see it perfect. Thank you.
Okay, good. Hi, everybody. My name is Konstantin Bukhryakov, and thank you for Lorianne for invitation to this webinar series. And this is very, it's my pleasure to be the first speaker of this cycle of webinars. And today I'm going to talk about homogeneous catalysis by organometallic complexes. And my talk is give me a sec. Okay. So my talk will have three parts, and the first part will be about catalysis in general. So I'm going to give you some general information about catalysis, homogeneous catalysis versus heterogeneous. And then we're going to talk about types of homogeneous catalysis. And the last part of my presentation, I will give you some updates, some insights of my own research related to homogeneous catalysis by molybdenum complexes. So let's start our first part about catalysis. So the catalyst, it's a substance which speeds up the reaction, but it does not really undergo any permanent changes by itself. And this is a good analogy. I really like this picture. This is a good analogy of a catalyst. So this person is a catalyst who helps our reaction to climb a rock, right? And the position of this person doesn't really change during the catalysis, right? But you can envision how this one person can help many other molecules, many other person to climb a rock, and speeds up the overall movement. And since our catalyst doesn't really go any permanent changes, catalysts don't appear in the overall balanced equation. And there is a lot of types of catalysts available, but fundamentally they're not much different, and they have a very similar, like, fundamental mechanism of how they work. And basically all catalysts, they work by reducing energy barrier of our reaction. So let's take a look on energy diagram of our reaction. So X, Y, it's our starting materials, and Z, our product. And for reaction to happen, those X, Y should collide, should form some transition state, which has very high energy, and we call this energy that our starting material, our reaction should overcome energy barrier. So in absence of catalyst, this barrier is high, but in presence of catalyst, these barrier become lower, and usually catalysis happen in a few steps, so it's not one step anymore. So the mechanism, catalytic mechanism, could be quite sophisticated, complicated, but you can see there is a few intermediates and few transition states formed during the reaction. And but overall, our catalysts reduce the energy barrier, the energy what we need to spend to move reaction forward. So, in other words, our catalyst stabilize transition state, right? It make our transition state less energetic. So as you can see by this energy diagram, the catalyst does not really change effect thermodynamics of our reaction, right? Because of delta G, this free energy change is the same, and it depends only on energy of our starting material and product, right? But catalyst affect kinetic of the reaction by because it's speeding up the reaction. Okay, so even though there is fundamentally the catalysts are similar, right, in terms of how they work, but there is some difference between them. And there is two big groups of kinds of catalysts: homogeneous catalysts and heterogeneous catalysts. And homogeneous catalysts, our reactants and catalysts are in the same phase. And the good real world example would be fermentation of sugar, conversion of sugar to ethanol by enzymatic fermentation to make a wine, right? So our catalysts, which are enzymes, which some microorganisms contain, they're in the same phase as our sugar, in aqueous phase, right? It's solution, and the catalysis happen in the liquid phase. The heterogeneous catalysts, they're in different phase, and a real world example would be the catalytic converter in our cars. So if you use a car, all cars have this catalytic converter. This is some small box in our exhaust, right? Which catalyze oxidation of hydrocarbons, CO, and nitrogen oxide gases using platinum, palladium heterogeneous catalysts, right, to make CO2 in water. So by implying these catalyst converters, we are reducing the pollution, and which is great for environment. So let's take a look in more details. What is the difference between heterogeneous and homogeneous catalysts? So reaction in heterogeneous catalysis, our reaction happens in interface, and usually we talk about surface, right? But it also could be two non-miscible liquids, right? For example, organic phase and aqueous phase, and reaction will happen in an interface of those liquids. But most of the time, when we talk about heterogeneous catalyst, we talk about solid catalyst, and our starting material or our reactants are in a gas or liquid phases. In homogeneous catalyst, reaction happens in the same phase, and it's usually gas or liquid. So since the catalyst happens on the surface, we have to be aware that not all those atoms on the surface are catalytically active, right? So we have only a small fraction of these active sites on the surface which catalyze the reaction. And in terms of homogeneous catalysis, catalysts have a molecular structure. So the precise structure of surface is very often unknown, and it's really hard to study. So we have to, it's hard to figure out where our active sites is located, what is the structure of active sites, how it works, what is the mechanism of the reaction. In contrast, our homogeneous catalysts, they have a known structure. It's relatively easy to figure out the structure of your catalyst by X-ray or NMR studies. So for homogeneous catalysts, we know the precise structure of catalyst, and we can actually figure out the mechanisms of the reaction. So since it's hard to study, it's really, for heterogeneous catalysts, it's hard to figure out what is important for catalysis. So what we should change to make our catalyst more active or selective. And usually people who are doing heterogeneous catalysis, they're doing just combinatorial search. So they just change some conditions, how they prepare the catalyst, and see how those changes affect the catalysis. But for homogeneous catalyst, since we know the structure and we can precisely change each part of the catalyst, we can figure out what is the structure-activity relationship for our catalyst, and the catalysis, right, could be rationally designed. And in the last part of my presentation, I will give you example how the understanding of the mechanism and structure of catalyst help us to prepare some new catalyst for particular applications. Another thing about heterogeneous catalyst, we have an additional diffusion barrier. So since it's a surface and our reactants in a liquid, for example, our reactants should diffuse to the surface. They should sorb, bind to the surface. There is some catalysis happen, and they should desorb from the surface, right? And this diffusion barrier sometimes give, when it's a rate limiting step, right, it significantly affects the overall rate of the reaction. And in homogeneous catalysis, there is no such diffusion barrier. So sometimes homogeneous catalysis has a higher rate. But since heterogeneous catalyst is in different phase, so our catalyst and reactants in different phases, it's easy to remove after reaction. The catalyst, it's easy to remove after reaction and reuse. And for homogeneous catalysis, additional purification step is required to remove our catalyst after the reaction mixture, after reaction done. And it's often, most of the time, it's not reusable. Even though in some cases it could be reused, but most of the time it's not reusable. So in terms of applications, heterogeneous catalysts are great for industry. So more than 90% of chemicals in industry made using heterogeneous catalysts. And there's a few extremely important applications of heterogeneous catalysts in industry. So first, it's a Haber-Bosch process, which produces 140 million tons of ammonia from nitrogen from atmosphere. And this ammonia is used to make fertilizers to feed our growing human population. So it's extremely important for sustainable world right now. The second very important application is olefin polymerization, and most of the plastics that we use on daily basis are made using a heterogeneous catalyst. And the third important application is the cracking, catalytic cracking of crude oil, so which used to convert crude oil to the valuable chemicals and gasoline. And just in the United States, every day, 5 million barrels of crude oil is converted to those chemicals using this process. And there is a lot of other very important heterogeneous catalyst applications. Homogeneous catalysts, so why they're important, how we can apply them. And they're great to understand the mechanism, right? Since we know the precise structure of catalyst, we can figure out the mechanism. And ultimately, we can apply this knowledge to develop a new heterogeneous catalyst. And the most active and selective catalysts are enzymes, and they're homogeneous catalysts. And the most active enzymes can catalyze up to 10 million reactions per second, which is unachievable, completely unachievable for synthetic artificial catalysts, what human can make. So most important application is, of course, life process. So life by itself is possible because of enzymes, right? Because of millions of reactions right now catalyzed in your body by enzymes. In terms of synthetic applications, they are great for research and development. So I was working in pharmaceutical industry where I was developing new drugs. And we use a lot of homogeneous catalysts to make a library of biologically active compounds. And also in industry, homogeneous catalysts used to make fine chemicals. So fine chemicals, it's chemicals which complicated, which are made in many steps, complicated synthesis, but we need it in some limited amount, for example, to treat some rare disease, for example. So let's now talk a little bit about types of homogeneous catalysts. So there is a few, the most important types of homogeneous catalysts. And first one is acid-base catalysis. And the mechanism is based on bond polarization. And as a catalyst, people use a Bronsted or Lewis acid and bases and organocatalysts. The next very important type of catalysis is transition metal catalysis, which is utilized unique electronic structure of transition metals. And there's two types. It's purely inorganic catalysis or organometallic catalysis. And organometallic complexes are complexes which contain metal-carbon bond. And so those organometallic catalysts are very important for modern organic synthesis because it can form carbon-carbon bonds. Enzymatic catalysis, which is utilized the 3D structure of proteins to bind to substrates, and other types of catalysis, which is phase transfer catalysis, photocatalysis. All of those are like a large area of chemistry, and of course, today we won't be able to cover all of them. But I'm going to give you a little bit overview about acid-base catalysis, just to give an example how acid catalyzed reaction works. So, for example, hydrolysis is a very simple acid catalyzed reaction. So our ester does not react with water at a neutral condition, but when we add some acid, right, it starts to react with the water to produce a carboxylic acid and alcohol. And the reaction goes through the protonation of carboxylic oxygen by proton, and we increase the electrophilicity of carbon atom in carbonyl group, and now our nucleophile, which is water, can attack our carbonyl carbon atom to form a carboxylic acid. Henry reaction would be a good example of base catalyzed reaction. So, and this is reaction between nitroalkanes and carbonyl compounds, and reaction proceeds through the deprotonation of one of the hydrogen on a nitroalkane to produce this carboanion, which is now nucleophilic enough to attack our electrophilic carbon center on carbonyl compound. And the stereospecific Henry reaction would be the great example of organocatalysis for two reasons. First of all, because it's a tandem catalysis. So in our catalyst, we have two groups. One is acidic group, which is thiourea, which can activate our carbonyl compound, and our amine group, basic amine, which now can activate our nitro alkane, right? And this catalyst is chiral, and it catalyzes reaction in such a way that only one enantiomer out of 4 possible is formed. Transition metal catalysis, and this is right now in organic synthetic chemistry. This is very important types of catalysis, and to highlight the recognition of this type of catalysis, there is a few Nobel Prizes were awarded in the last 2 decades for developing of this transition metal catalysis. So the first one is asymmetric hydrogenation, where we using ruthenium, rhodium, or iridium-based catalyst, we can add a hydrogen to the carbon oxygen or carbon double bond to make only one enantiomer, to make it enantiomer selectively. Olefin metathesis, which I'm gonna talk in more details in my third part of this talk. It's generally catalyzed by ruthenium, molybdenum, and tungsten-based catalyst, and where we can swap those groups between 2 olefins. And the third type is a cross-coupling reaction, which we use a palladium and nickel-based catalyst to form the carbon-carbon single bond. And this reaction is very important to make in pharmaceutical industry, to make a lot of drugs and for drug development. So this was like a general information about catalysis and homogeneous versus heterogeneous catalysis. And right now, I'm going to talk about my own research, which I did at MIT in a group of Professor Schrock, and which is related to olefin metathesis catalyzed by molybdenum alkylidiene complexes. CF3 olefins are very important functional groups in pharmaceutical industry because they have very interesting properties. They exhibit some interesting binding with the receptors. They are stable to metabolism, but unfortunately there was not much developed methods to install of CF3 olefin groups. And there are shown 4 main general reactions how to make these CF3 olefins. First 2 methods allowed to make only Z and E mixture of trans and cis olefins, and they are not selective. The third method produces only trans E isomer, but it requires of using trifluoroiodomethane, which is a gas, and it's not really convenient to work with. And only the third method allows to make exclusively Z on E isomers, depending on starting materials. But those starting materials are by themselves are quite hard and tedious to make. And taking this into consideration, olefin cross-metathesis would be very desirable strategy to make CF3 olefins for a few reasons. First of all, for this particular reaction, right, when we just swap those groups between 2 olefins, doesn't produce any waste. So it's very atom economical. This CF3 ethylene is a non-flammable, commercially available liquid, it's easy to handle and safe to handle, but it were not many examples in organic chemistry of utilizing of this CF3 ethylene, and there was no examples for olefin metathesis. And in order to understand why this compound was not applied for olefin metathesis, let's take a look on mechanism of our olefin metathesis reaction. So the catalyst for olefin metathesis contains metal-carbon double bond, and we call this group alkylidene. In the first step, our alkylidene reacts with the olefin, and usually our electron-rich olefin binds to the electron-deficient metal center to form an olefinic complex, which now can form metallocyclobutane. And now, after cycloreversion step, so if our metallocyclobutane decomposes in this way, it will produce us initial complex. But if it produces if it decomposes in this way, it will produce a new olefin, a new alkylidene. So new alkylidene can react with the second molecule of olefin, form metallocyclobutane, form the second molecule of product, and regenerate our alkylidene. So the first person who proposed this mechanism was French chemist Yves Chauvin. Richard Schrock was the first who developed molybdenum and tungsten-based catalyst for olefin metathesis, and Professor Robert Grubbs was the first who developed a ruthenium-based catalyst for olefin metathesis. And all of them received a Nobel Prize in 2005 for developing of this reaction. So let's come back to our BCF3 olefin. So let's take a look on the first step of this reaction, right? So here's the structure of one of the most active Schrock catalysts, molybdenum alkylidene catalyst. And the structure of this catalyst is a little bit complicated, but we're gonna talk about this structure in details in a little bit. But for now, I just wanna point out that this compound has a monoaryloxide pyrrolite group, and we call this complex MAP complex. So let's take a look what happened when our BCF3 ethylene react, how it will react with our complex and form our olefinic complex. Right? So this would be the structure of our olefinic complex, but this is not what happened. And this doesn't happen. This doesn't happen for two reasons. First reason is that I said previously, usually electron-rich olefin binds to electron-deficient metal center, but CF3 groups are electron withdrawing, and our olefin by itself is electron-deficient. And additionally, you see there is a lot of things around molybdenum center, right? So it's kind of sterically hindered, right? And our CF3 groups it's kind of big. So this doesn't happen also for steric reasons. So how we can overcome these challenges? What we can do to make this happen? First, we can increase electrophilicity of metal center even more. And second, we can decrease the steric hindrance around the metal. Around the same time, when I joined the Professor Schrock group, one of our postdocs discovered this reaction. And he discovered that if we take a MAP complex and react it with the pyridinium chloride, so our pyridinium can protonate pyrrolite to make a new class of compounds, which now would be called monoaryloxide chloride complex or MAC complex. And the chloride is a more electron withdrawing compared to pyrrolite, and it's a smaller. So this MAC complex would be ideal candidate to try reaction with BCF3 olefin. And indeed, this is the first reaction, olefin metathesis reaction involving BCF3 olefin, BCF3 ethylene, and it is catalyzed by MAC complex. So this MAC complex has is extremely interesting compound, which should be developed even further, but unfortunately we didn't have a reliable way how to make this catalyst. So initial synthesis of this catalyst includes 4 steps and the 6.5 overall yield, which is very low. So we didn't have a reliable method of making those highly active catalysts, right? And of course, we couldn't make it in a large scale, and we couldn't utilize it to the solving of real world problem, for example, to make some drugs. So, and my project was, one of my projects was to develop a new method of making Mach complexes in more efficient way. So I developed a method starting from this alkyl disamide complex 1, which can react with HCl in presence of phosphine and produce a bis chloride complex 6. So here is the crystal structure of this complex. And this compound can react with the lithium aryl oxide to produce desirable Mach complex in a good yield. So as a result, this is to date, this is the shortest way to make Mach complexes, and we increase the overall yield in 10 times. And here is the crystal structure, one of these complexes. And I want to point out to one small detail in this crystal structure. So those crystal structures, they contain phosphine ligand. You see, there is a phosphine ligand here. But the Mach complex, which contains a phosphine ligand, is not catalytically active because the phosphine blocks the same site where our olefins should bind to the molybdenum. And why do we need this phosphine? And the answer is simple, because it helps us to isolate the complexes. So all those complexes are extremely sensitive to oxygen and water, and all reactions done in nitrogen-filled glove box. And the only available way how to make and isolate our catalyst is the crystallization. If catalyst is not crystalline, we cannot isolate it, right? And this phosphine, it makes our catalyst is more crystalline. So this is a purpose of this phosphine. But as I said, we don't need this phosphine for catalysis. So before the catalysis, we have to activate our catalyst. We have to remove this phosphine to open up this site on molybdenum for binding to olefin. We usually use Lewis acids, which we call the phosphine scavengers. So the phosphine scavenger to scavenge our phosphine, make a 4-coordinated catalytically active Mach complex. And these Mach complexes can catalyze the reaction with BCF3 olefins, but it has some limitations. So first of all, it cannot catalyze the reaction with terminal olefins because the second product of this reaction is ethylene, and Mach complexes are generally not stable under ethylene condition. And the second, this Mach complex cannot catalyze the reaction with the sterically hindered olefins, for example, 3-substituted olefins, right? So in my next project, my next goal was to develop a new catalyst which can overcome those challenges. So, but how we can improve our catalyst? Right? So let's take a look in details on each part of our catalyst. So one part is alkylidine, right? And we know this alkylidine is extremely important for catalysis, but as you saw in catalytic cycle, alkylidine group is constantly swapping, right? It's constantly changing during the catalysis. And the nature of alkylidine doesn't really influence catalysis itself. Chloride, and we already know we need chloride for this unique mode of reactivity. This large aryl oxide. Why do we need this? Why do we need this aryl oxide? And we need it for selectivity, because of this large bulky aryl oxide pushes the formation metallocyclic butane in such a way that all substituents will be in cis position. And there is an after cycloreversion step when our cyclobutane will decompose, we will form only cis olefin. So we need it for selectivity. And the group which we actually can change now, right? Try to change. It's amide group. And we decided to change this bulky adamantyl amide group to pentafluorophenylamide for 2 reasons. First of all, this group is more electron withdrawing, right? So it can increase electrophilicity of metal center even more, and our catalyst will be even more active. And the second, pentafluorophenylamide is planar, right? So it's less sterically hindered compared to aryl adamantyl group. So utilizing the same method which we developed previously, starting from bis-alkyl bisamide complex 8, we made the bis chloride complex 9 in acceptable yield, and then we react with bis chloride with lithium aryl oxide to make our MAC complex 10. And today, this is not only the shortest way of making this type of complex, but it's only available way, because the initial synthesis did not allow to make a pentafluoramide MAC complexes. Here is the crystal structure of one of those complexes. So again, we have a phosphine here, which we need for crystallinity of our complex for isolation. Okay, so we tried our newly prepared catalyst for catalysis. So we use a 5 molar % of catalyst. We add a little bit more of our phosphine scavenger to scavenge phosphine and activate catalyst. And unfortunately, the yield was only 5%. We prepared a library of different MAC complexes varying with bulky aryl oxide to see how those aryl oxides will affect our catalysis. And it turned out that in all cases, the conversion was only 5%, except this very bulky hexaisopropyl MAC complex, which gives a full conversion after 1 hour. And the reason of this reactivity is following. So after the first catalytic cycle, we generate one equivalent compared to catalyst, based on catalyst of a product and CF3 alkylidine. And it turned out this CF3 alkylidine is extremely unstable and it quickly decomposes in most cases, and only in case of hexaisopropyl terraphenoxide, this alkylidine is stable enough to continue the catalytic cycle. So we tested the scope of our newly prepared catalyst, so it can successfully catalyze reaction with Z and E olefins. There is some functional group tolerance, so we can use an ester group with a good activity and moderate selectivity. And additionally, this is the only known and available catalyst to date which can catalyze reaction between this CF3 olefin and terminal olefins, alpha branch terminal olefins, 3 substituted, and even 4 substituted olefins. So as I said, this is only available in known catalysts which can catalyze this reaction. So in the summary of this part, I've shown you how the understanding the mechanism and how our reaction work, we were able to design and develop a new catalyst for particular applications. So this is about the end of my talk. I just wanna thank you to my group, so my research group at FIU. So right now I'm an assistant professor at FIU, where we develop a new catalyst, but now we are developing iron and vanadium-based catalyst and molybdenum-based catalyst as well for olefin and alkyne metathesis. And we are actively looking for graduate students. So if you are thinking or considering PhD, pursuing PhD in chemistry, and you interested in organometallic chemistry and catalysis, please send me an email and we will discuss further about our opening position in our group. So right now, I just want to say thank you for listening, and please, yeah, I'm open for questions.
Thank you so much for that excellent talk. We do have several questions for you. Firstly, how do you control the selectivity for your reaction? You mentioned the diffusion barrier in heterogeneous catalysis, but what are the limitations in homogeneous catalysis?
What are limitations in homogeneous catalysis?
Yes.
In terms of, in general or in selective? In
terms of selectivity for your reaction.
So in all for selectivity, as I shown in my last part of presentation, I show how we can change some ligands around the metal center, for example, to achieve the desirable selectivity. So as I said, the homogeneous catalysis is it could be rationally designed, and we can, after we figure out the mechanism, we actually can design a catalyst which would be both selective and active. In terms of some limitations of homogeneous catalysis as compared to heterogeneous, it's not only we can reuse heterogeneous catalysis, right, and recycle them, but also stability. So often heterogeneous catalysts in industry, they can tolerate high temperature and pressure, and it's very rarely for homogeneous catalysis. So it's usually homogeneous catalysis that quickly decomposes at high temperature. And the main reason, for example, for transition metal catalyzed reaction, the main reason is a bimolecular decomposition. So when two catalysts come close together, so metals tend to aggregate, so they form nanoparticles at high temperature. And there are many types of decomposition pathways which I know. Yes.
Thank you. Could you please comment on why your new catalyst was able to catalyze the terminal alkenes, but your older one was not?
Great question. So the Mach complexes in general, they are not stable to ethylene. And can I go to my slides? Oh, no. Can I go to my slides?
You should be able to share your screen.
Okay, give me a second. Okay, yes. Okay, so let's take a look on our olefin metathesis mechanism. So when our X is H, right? So this would be the ethylene, and R is H, right? So we form metallocyclobutane, which doesn't have any substituents except H's. So it's all H. So all groups R and XX will be hydrogens if our catalyst reacts with ethylene. And this metallocyclobutane is not stable. It quickly decomposes for Mach complexes. It's known. So this complex quickly decomposes. Yeah. So this complex quickly decomposes when it's formed metallocyclobutane without any substituents. So our new prepared catalyst, it also decomposes. So this catalyst is also decomposes under ethylene condition, but because this catalyst is much more active, so the catalytic pathway is faster. The rate of catalysis is higher compared to rate of the decomposition. So this catalyst is so active that it has time to catalyze, to complete the reaction before it decomposes under ethylene condition.
That makes sense. Thank you. Could you explain how the phosphine scavenger works?
Oh, sure. So our phosphine, it has a, so let me open it up. Yeah, so our phosphine has a lone pair, and our Lewis acid has a vacant empty p orbital. So basically, this is just very simple Lewis acid base reaction. So our phosphine gives the lone pair to empty p orbital on the boron, right, to form this complex, which is very, very stable, right? And So this is how it works. So it's a scavenge our phosphine. It binds to the phosphine irreversibly.
Okay, thank you. Do you have any suggestions on methods to prevent metal plating out in homogeneous catalytic systems in industry?
Metal what?
Metal plating out? Perhaps they could rephrase their question and we'll get back to it. Here's another one. You have suggestions to crystallize organometallic complexes from solution?
Suggestions?
Yeah.
It's a general suggestion. It's increase the coordination number, like around the metal center. For example, when we remove a phosphine, right, this complex is a 4-coordinated. It has a four groups around. And generally, when we have a fewer groups around the metal center, the complex is more soluble and less crystalline. So by adding those neutral ligands, for example, phosphine, we increase the coordination number around the metal center. Now it's 5, and 6 would be even better. So for example, in this case, so this 9, so it's an octahedral geometry. So it's a 6 ligands around the metal center, and usually this is the best. So this is the best for crystallinity. Okay. So the general idea, add some neutral ligands to increase the coordination number around the metal.
Okay, thank you. And could you comment on how you got percent yields for your metathesis reactions or any of your reactions?
I've got what?
How you got obtained your percent yields?
Percent yields?
Yes, yeah.
So those reactions done in NMR tube. So it's in a daturated benzene. And we usually just mixed everything together and daturated benzene and check NMR after 1 hour. And we compare signals of starting materials. We usually use olefinic signals, which are very characteristic. It's about between 5 and 6 ppm in NMR. So we compare the signals of those hydrogens and olefinic signals in starting material and a product. They are very distinguishable. And most of the cases, we don't see any starting material. So in all those cases, we usually indicated 99% when we don't see starting material in by NMR. And this is not isolated yield. This is a conversion by NMR. And this is, for example, I highlighted here. So it's a conversion.
Thank you. And last question, do you have any suggestions for increasing the reusability of homogeneous catalysts?
Oh, yes. So the usual method, the common strategy is to make supported homogeneous catalysts. So for example, we can covalently bind our homogeneous catalyst to some support, for example, polymer. So merifilk resin, for example, would be the example of supported catalysis. So we bind it to some polymer, and after the reaction, we just filter out this polymer and use it again.
Awesome. Thank you so much. So I have one concluding slide for everyone. Thank you so much, Dr. Bukhryakov, for giving your time and donating your knowledge and presenting this excellent lecture. We all really appreciate it, and I'm sure we've learned a lot from it. I know I have.